This resource is the second in a three-part series on solving triangles, or finding missing information for a triangle given some combination of side lengths and angle measures for any triangle. Part 1 considers the law of sines. We define the law and provide the situations to which the law best applies. We look at an example of each case. Part 2 considers the ambiguous case, where the provided information allows one solution, two distinct solutions, or no solutions. We consider examples demonstrating each case. Part 3 considers the law of cosines. We define the law and suggest its best use. We look at examples for each case. One situation where we will use the law of sines exclusively to solve our triangle is the case where we know the lengths of two sides and one angle measure, but that angle is not between the two sides. This situation is often referred to as the swinging gate. This name will make more sense as we go through the possible outcomes of this situation. Wait a minute, outcomes? Like more than one? But this is math. There should only be one answer. Well, in this side-side angle setup, there are actually three possible outcomes. There may be one triangle we can solve for, or there may not be a triangle possible at all, or there may be two distinct triangles. Let's see how this happens, shall we? To determine whether the given information leads to one, two, or no possible triangles, we need to go through a solution algorithm. First, set up the law of sines with the information we have. Then we will cross multiply and divide. When we do so, we are solving for the sine of an angle. Inspect the result. If the amount is greater than 1, then no triangle is possible. If the result is less than 1, proceed. Take the inverse sine of the result. This gives us one possible measure for the angle. Because sine is positive in the first and second quadrants, we may have another possible solution. We need to find the quadrant 2 version of the angle. So we subtract that amount from 180 degrees. To see if this is a reasonable answer, we add this second version of the angle to the angle measure we knew at the start. If that sum is greater than 180, only one triangle is possible. If the sum is less than 180, we have two viable triangles. Let's look at some examples and try to make some sense of this strange situation. Suppose we know that the measure of angle A is 57 degrees and that the lengths of the side opposite, little a, is 33. We also know that little b is 26. With this setup, how many triangles are possible? Set up the law of sines ratios. We have the angle A and the length of the side opposite, so we will use that as our basis for the ratios. Since we know little b, we will work to find the measure of angle B. So we have 33 over the sine of 57 equal to 26 over the sine of angle B. We cross multiply and divide to solve for the sine of angle B. Using available technology, we find that sine of B equals 0.6608. We have at least one triangle possible, so we continue on our mathematical journey. To find the actual measure of angle B, we take the inverse sine of the decimal amount. This gives us B equal to 41.4 degrees. We may have more than one triangle possible. We need to find this other potential version of angle B. To do so, we subtract the 41.4 from 180, which leaves us 138.6 degrees. To see if this second version of the triangle is legitimate, we add the second version of angle B to the angle we knew from the start, angle A. we have 138.6 plus 57, which adds to 197.6 degrees. Because this amount is more than the possible degree total for the angles of a triangle, we know that there is only one triangle possible. We would then use the same methods as before to find the final missing angle and length to finish solving the triangle. Let's look at another example. Suppose this time angle A was 50 degrees, little a was 10, and little b was 20. How many triangles are possible with this setup? We set up our ratios as before. Cross multiply and divide. When we do this arithmetic, we find that sine of angle B equals 1.532. Because the largest value sine takes is 1, this value is impossible. Therefore, no triangle is possible that has the given measurements. What if angle A was 35 degrees, little a were 12, and little b was 16? How many triangles are possible now? We set up the ratios. 12 over sine of 35 equal to 16 over the sine of angle B. Cross multiply and divide. This gives us sine of B equal to 0.7648. Since this is less than 1, at least one triangle is possible. We take the inverse sine of the decimal amount to find that angle B is 49.9 degrees. At least the first quadrant version of angle B is 49.9 degrees. We subtract that amount from 180 to find the second quadrant version. Angle B version 2 equals 130.1 degrees. To check if this leads to a second possible triangle, we add the original angle measure we were given. 130.1 plus 35 is only 165.1. Because that sum is less than 180, we can create two possible triangles with our original information. In fact, we have all the information we were missing. Note that side BC, which we called little a, swings inward to form the second possible triangle. That side acts like a swinging gate door. The ambiguous case for solving a triangle is when we are presented with the lengths of two sides and the measure of the angle not in between the two sides. This case allows for three potential types of solutions. Either there will be exactly one triangle possible, exactly two triangles possible, or no triangles possible. To determine which case we are faced with, first set up an appropriate law of sines proportion. Cross multiply and divide to solve for the sine of a missing angle. If that amount is greater than 1, no triangle is possible, and we cannot go any farther. Otherwise, we take the inverse sign to find the first possible value for the angle measure. Then find a second version of the angle by subtracting from 180. To check if the second option is viable, add this second version angle measure to the angle measure we were originally provided. If that sum is less than 180, two triangles are possible. Otherwise, only one triangle is possible. But what happens if we know two sides and the angle in between them? Or we even know all three lengths? Stay tuned to find out about the law of cosines.